Thank you very much. So we are mainly interested in my group on the study of reactivity in supercritical fluids and the associated technology for the design of advanced nanostructure materials, but also material recycling, which is the topic of today. Thank you very much. No, it's okay. Just the pointer. I would like first to thank my co-workers on this project, Cédric Slotowski, Anne Serrani, Maxime Antal, Antoine de Beauvais, and Christelle Morin. The first application, one of the first applications of supercritical fluid technology in the field of material recycling was in the solvolysis of plastics in near and supercritical fluids, with a famous example of the recycling of PET bottle. And it was mainly done in Japan in the beginning of the 90s. Our Japanese colleagues proved that it was easily to depolymerize PET into the monomers. And about 10 years ago, I would say the whole community came to another problematics, the solvolysis of thermosettings resin in near and supercritical fluids. And again, the Japanese community was very active in this field, but also the European one, mainly at the University of Nottingham and at the University of Bordeaux. And in Japan, as you can see, they are already working at a relatively large scale with a pilot scale facility. You see in a batch 400 kilograms of glass fiber which can be recovered. And now we see more and more articles coming in the field of the recycling of inorganic materials in hydrothermal condition, with the example of printed silicon board, the example of solar cell, and so on. Today I'm going mainly to focus my presentation on what we did in the field of the recycling of thermosetting resin, with one objective to recover carbon fibers from carbon fiber reinforced composite. For this, I propose you the following outline. First, an introduction to supercritical fluids and its development in France, to show you that we have an important, at that time, industrial technological support to push this recycling technology. And after, I'm going to speak about the recycling of CFRP using the supercritical fluid technology. So, a supercritical fluid, for the chemist, as you can see on this diagram, pressure as a function of temperature. This is just a solvent you are using in specific condition of pressure and temperature, at a pressure which is above the critical pressure of the fluid, and at a temperature which is above the critical temperature of the concerned fluids. And what is very interesting with this kind of fluids, as you can see with the red arrow, you can precisely tune the properties of your fluid, just changing pressure and temperature. And you can tune these properties from the properties of a liquid to the properties of a gas. As you can see here, as example, with the density, viscosity, and diffusivity. I'm going now to show you a movie. In fact, you see here, one of the most famous supercritical fluid is carbon dioxide. So this cell is filled with carbon dioxide at the critical density. So this means, if you're on the curve, we are here, we are going to heat up the cell and move along the equilibrium curve, arrive to the critical point, and go to the supercritical domain. So, supercritical CO2 is easy because critical temperature is 31 degrees Celsius. So this means you can heat the cell with the end. So we are heating the cell. We speed up a little bit the movie. So the meniscus is disappearing. And you see we are homogeneous. We are in the supercritical condition. And now, so it seems to be homogeneous. And this is generally what people said. And after, we are cooling down, and you see there is a nucleation and growth of liquid droplet, and again, the formation of the meniscus. So it seems to be homogeneous. But if you are looking at the microscopic scale, it's heterogeneous. You see, the organization in a supercritical fluid is like this. You have some domain in which density is like a liquid, and some domain in which density is like in a gas. And this allows to explain this hybrid behavior between the liquid and the gas, and the possibility to adjust continuously the properties of the fluid from the properties of a liquid to the property of a gas. So this is valid for all the fluid under supercritical condition. Water is a very good solvent and exhibits specific properties due to the hydrogen bonding. There is no in other kind of solvent like CO2, for instance. And this solvent we have used to develop our technology for the recycling of carbon fiber from CFRP. Now you see, it's much more difficult as a technical point of view in comparison with CO2. The critical temperature of water is 374 degrees Celsius, and the critical pressure 221 bar. But as I told you, so we see the possibility to change the properties, also some domain with liquid-like density, some domain with gas-like density, but we have also other interesting properties which can be used for chemistry. And this one is very interesting. You see, this is the evolution of the ionic product of water, decomposition of water into H plus and OH minus. So you know, 10 to the power minus 14, and if you increase temperature, you are reaching 10 to the power minus 11. This means 3 orders of magnitude higher than the one of water at room pressure and temperature. And after, when you are crossing the critical points, it falls down to 10 to the power minus 24. So this means you can play with chemistry around. And another very important property, this is this one, the evolution of the dielectric constant. So everybody knows that water is a polar solvent, but under supercritical condition, you see here, it's a solvent with a polarity like hexane. So this means you can solubilize in supercritical water some organic molecule. And thanks to these properties, so you can perform reaction in homogeneous media. Consequent is fast kinetics, so generally time process are low, and you can use a continuous process. Of course, due to the topic of today, you can make hydrolysis of molecule, and especially we are going to speak about hydrolysis of epoxy resin. And it's considered as a sustainable technology. Why? Because from the beginning of the development of this technology, in the 70s, it was supercritical fluids was generally used to substitute more toxic organic solvent. And a last interesting properties, due to the change of dielectric constant, you can recover inorganic particles. So you can solubilize organic molecules, but you can also precipitate inorganic molecules. And I'm going to show you a movie. So this was made in a synchrotron. This is an in situ experiment. And I'm going to show you the precipitation of sodium chloride, if it wants to work. No, it doesn't work, but it doesn't matter. So what I wanted to show you, so we are heating the solution which contains sodium chloride under the beam, and you can see the formation of the precipitate and at the same time the nature of this precipitate. So just to illustrate the fact that you can also precipitate, if necessary, inorganic material. So thanks to this specific properties, different kind of technology have been developed since the beginning of the 19th. So the first application was supercritical water oxidation for wastewater treatment. We are doing a cold combustion below 600 degrees Celsius of the organic matter, adding oxygen. And all the community switched from a philosophy of destruction to one of valorization through the thermochemical conversion of biomass, liquefaction to gasification. So we study the correlation between the structure of the biomass and the obtained product as a function of the position in the phase diagram. And also the recycling of composites, which will be the topic of today. And in terms of development, we can today handle supercritical fluids at different scale, as you can see, from microscale. We have developed some microreactors which can operate under pressure and temperature. So this means now we can process supercritical fluids into microreactor. And this is very powerful to make some in situ investigation, as you have seen, for instance, with in situ sacs and wax investigation in synchrotron. This is a conventional lab scale facility. And here, our successful technology transfer in the field of supercritical water oxidation. So this company was founded in 2008, and there are now 30 employees trying to exploit this technology in the field of hazardous wastewater treatment. And this is an important point because this company can support our technological development in the field of the recycling of composite materials. So we came to this about in 2008 when the Airbus plane manufacturing came to the lab and say, could you do something to help us? And in fact, they came because we made some tests in 2000 on just epoxy resin. And we showed that at that time that it was possible to solubilize, to hydrolyze very easily some epoxy resin into supercritical water. And they say, okay, but we need to work on a real waste. This means a mixture. You can see a different kind of material. For the polymer matrix, it can be thermoplastics, it can be elastomer, and of course, the thermoset. So this means a mixture. For thermoplastics, it was known that it was no problem to transform it into supercritical water, so we work on elastomers. Regarding the reinforcement, we focus on carbon fiber because we did, at that time, it can work with a glass fiber, but as an economical point of view. We cannot believe that this kind of innovative technology can be economically self-sufficient if you recover glass fiber. But as a technical point of view, I would say it works. For the polymer, so it can be inert materials with a polymerized matrix or not polymerized matrix. And this project was supported by, as I told you, these companies, so the Airbus plane manufacturer, the company Heracles from the Safran group. So Safran is a big French company, more than 60,000 employees all over the world, and some people from the Airbus Space and Defense company. And this was also supported by the French agency ADEME. Regarding the deposit, so our colleagues spoke about the sources in UK. In the frame of our project, it was concerned, of course, production scraps from the Airbus company. It was also concerned military dismantling. On the place of Bordeaux, there was, because we have numerous industry from space and defense industry, and they built together a platform to try to propose a sustainable way for military dismantling. And the consequence, they have some material to treat. And of course, last point was aeronautic dismantling, but at that time, there are not so many composites into the airplane which are dismantled. Now, what do we need to recycle carbon fiber? I think it's not necessary to present this because Professor Mantevengo did this very deeply and very well just before me. We have hopefully the same motivation. Perhaps I could just mention that there is a need, of course, for the airplane manufacturing industry, but also now in the car industry, because now the car manufacturer BMW is selling 2 cars on the market using carbon fiber. The i8 you can see here, and also the i3. Regarding the chemistry, so we did the experiment on our lab scale facility. This is the solvolysis reactor, and in terms of principle is relatively easy. We put the composite material into the reactor, and we are just making a reactive extraction. We are flowing into the reactor some water in specific condition of pressure and temperature, and at the end you can recover the carbon fiber, which are very clean. You see here the condition, about 400 degrees Celsius, 25 MPa, and reaction time is, as I told you, kinetics are fast, less than 10 minutes. So it's fast if you compare with other kinds of technologies. We made, of course, some mass balance. So as I told you, you put the composite and just water, and at the end, you recover the carbon fibers. Interesting point, there is no emission of gas due to the solvolysis reaction. 400 degrees Celsius is not so high. And you recover your organic resin into water. In terms of characterization, you see here some scanning electron microscopy picture of fiber before making the composites, and here fibers after the recycling treatment. And what you can see is that there is no destruction of the surface of the fiber. Surface of the fiber is very clean and is the same as the one before the treatment. Some colleagues from the mechanics of Bordeaux made some important tests because one of the motivations of this work, as I told you, we knew that the chemistry was okay, but we needed to prove that there was not a big effect of the treatment on the mechanical properties of fiber. So they did 3 kinds of experiments. Of course, the reference, new fibers exposed to supercritical water treatment, and the recycled fibers. So here are the results. So what you can see, there is not a strong impact on the treatment on the mechanical properties of the fiber. We are losing less than 5% of the mechanical properties of the initial material. It's between 1.7 and 4, knowing that it's difficult to make this kind of, to compare this result with the untreated fiber, because the untreated fiber has the size at the surface, and the treated fiber are this size. So this means we can consider that the supercritical fluid technology can really allow to recover clean fiber, keeping almost the same initial mechanical properties. So this is a very important result, and this has also been confirmed by other colleagues working on these topics. A very interesting result for the chemist. We proved that it was possible to be selective in the chemistry, and you see here a composite made with a Kevlar fiber, polyaramid fiber, into an epoxy resin. And it's possible to control the chemistry in order to just hydrolyze the epoxy resin and keep the polyaramid fiber. So as a chemist, we were very happy with this result. And you have here the proof with thermogravimetric analysis. You see here in the composite, you see here the resin, and after the fibers, and after the treatment, you have just the fibers. And we have now an end user for this kind of materials. And if you have a look on the scanning electron microscopy picture, you see that the surface of the Kevlar fiber are very clean, and there is again no aggression of the treatment on the properties of the surface of the fibers. A very important point that it was mentioned previously was energy balance, and in this kind of technology, more than 75% of the energy demand is coming from the water you need to eat, not pressurization. Generally, people think that pressure is energy. Pressure on this kind of technology is just 1% of the energy demand. Most of the energy is coming from water. That's why we work a lot to decrease the quantity of water you need for making the treatment. So we try to decrease, and now we know the quantity of water you need per kilogram of composite you want to treat. Environmental impact, that was also mentioned previously, is a very important point. So we did this in collaboration with Professor Guido Sonnemann, which just got a share on the University of Bordeaux to make life cycle assessment study. So he did this on technology, and you see here the graph for the composite, and as it was expected, the main impact is coming from the carbon fiber. As it was exposed previously, you need lots of energy to make the fiber. And you see here on the histogram the impact of the different contribution of the material. So in black, the fiber, the most important, and after the epoxy matrix and the injection process. So this is really a proof that we need, and it's a real need to recover this kind of material. And after, he compares two processes, landfilling, which is now one of the main issues for carbon fiber, with our technology. And you see here the results. Most impacting, of course, is landfilling. And you see in gray, with the different indicators, our technology, which is not so bad. After, as we discussed just previously, for me, energy demand is very important, but one important question is also the reuse of the carbon fiber, because now we know that it works, but to develop and to scale the process, we need to know the market for the reused. And for that, with a small reactor, we were producing just few milligrams of composite, so it was not enough for the colleagues working on the reuse of this material. So we can now operate this kind of facility. So it's 2.3 liter reactor, which allow to produce kilogram scale of fiber. And with kilogram scale of fiber, our colleagues from mechanics can develop some technology to reuse this fiber. And as you can see here, they succeeded to make the first product. But I think this point is also very challenging now, and is also very important for us to design our technology, to know what do they need in terms of length. Should we mill the fiber? Do we need 10 centimeter length fiber, and so on? So this is really some data we need to go further in the development of the technology. So as a conclusion, I spoke about the properties of supercritical fluids. I show that this can be. I say this can be because I'm convinced that there is not a unique solution, but this solution could be one solution for the recycling of carbon fiber from carbon fiber reinforced polymers. You have seen we can recover clean fibers through hydrolysis. Very interesting alternative to pyrolysis when you are looking at the evolution of mechanical properties before and after treatment. An important point for me is the possibility of treatment of multi-materials. You can put a composite which is a stick with steel, with different kind of material, and at the end you will recover the steel, aluminum and so on, and the carbon fiber. And as it was evaluated, a low impact on environment. So now we are on the way of pilot scale solvolysis reactor, and still information are missing, as I told you, for the need of the market for reusing this kind of material. To finish, I'd like to thank my co-workers, as I did at the beginning of the presentation, and I would like to thank you for your attention.
Thank you very much for your talk. Is there any question? Yes.
Yeah, thank you for this speech. What my interest is on the utility of this tool when it's come, if you want to use it for a community. What kind of community, for example, urban, where really the reuse and recycle is needed? What kind of, and how many people or inhabitants you can serve with this piloting you are making?
I'm a very small guy to try to answer to this question. Just working on science and technology.
Yeah, but science.
Yeah, you're right. Yeah. I think as it was shown in the keynote lecture of this morning, and as I show on many of my slides, if you are landfilling this material, you lose a very important part of energy. You put energy underground, with a huge impact in terms of CO2 footprint. So what we can do modestly as a scientific is to find a process, a technology which can allow to reuse these materials, knowing that if you see the evolution of the market for this CFRP, it's increasing a lot with the input of this kind of material into the automotive industry. And in 10 years, if you are looking at the evolution, if there is no solution, it could be really a problem. But I cannot tell you more. I'm sorry, because it's not in my field of competence.
I think it's there the gaps we need to really build, because when you are dealing with this technology, it's very useful.
Yes.
And, it's useful both for environment and for the society.
Yes, for sure.
So how can we make it useful for communities where we know that the dumping and build is really happening?
Yeah, for sure. And for this, we need to put around the table different field of competencies and people like you, for instance, who could help us to answer to your question.